Okay, third hour of Physics 1C for November 11th, November 1st. And we're talking now about the sources of magnetic fields. So we just learned about magnetic moments, and it's going to turn out that magnetic moments are effectively very similar to kind of what we're about to talk about, as in they are where magnetic fields come from. So magnetic fields basically come from moving charges or from electric currents, to say the simplest. The simplest way to put it is magnetic fields come from electric currents. They really come from just moving charges of any kind are going to produce magnetic fields, but electric currents are the main thing. Now, to talk about some of the just basic ideas about how this works, let's suppose that I have a wire, okay, and it carries an electric current that comes out of the page, like this right here, all right? One thing that we can do is we can go and we can set up little magnets around this, and what we'll find is that if I were to place a magnet like right here, the direction that the magnet would point would basically be like that. If I was to place a little compass needle right here, the direction of the compass needle would point this way. If I put a compass needle here, the compass needle would point this way. And if I put a compass needle here, the compass needle would point like that. Okay? So this is an observation that tells us that the type of magnetic field that is produced around a current-carrying wire tends to be kind of circular in nature, and it tends to look something like this. So if I have a current-carrying wire and it carries current out of the page, it's going to create circular magnetic field lines that are concentric around it like this right here. These are what the magnetic field lines look like. We actually have a setup in the lab where you can exactly see this, where we have current flowing straight up through a wire, and we can put little compass needles around it, and it proves exactly what we're saying right here. I'll try to show that to you tomorrow in class for those of you that are, or on Wednesday in class for those of you that are here if you remind me. Anyway, so this is the observation. Magnetic field lines tend to point in these kind of circles going around the current. And you can even predict for yourself what the direction would be. If you stick your thumb in the direction of the current, your fingers sweep around in the direction of the magnetic field. Again, this is a right-hand rule as well. So point your thumb in the direction of the current, your fingers will sweep in the direction of the magnetic field. Okay. I guess there's another one that I can mention, which is that we can actually kind of reverse this picture here. So if I give you a loop of wire like this, right, and it carries a current I, like that right there, it turns out that there's going to be a magnetic field at the center of this loop of wire, which looks very symmetrical with what I just showed you, and the magnetic field is going to point like that. Again, point your fingers in the direction of the magnetic field now, and you'll see that your fingers sweep in the direction of the current. So can you see this kind of the connection between these two pictures here? Current flowing out of the board creates circular magnetic field lines. A current that's shaped in the form of a circle is going to create a magnetic field that points like this at its center. All right. So we'd like to be able to come up with a mathematical way to describe this. And in order to do that, we're going to use something that's called the Biot law. The Biot law describes the size of the magnetic field that's created by a single current element, and it looks something like this. Let's see if I can write it down from memory. I have the book open, but I'm going to try to write it down from memory, and then we'll check. Okay, I think that's it. I got these backwards. It's ds cross r hat. Here we go. That is what we call the Biot law. It looks pretty damn confusing if you look at it. So let's talk about what it actually means. What this says is, suppose that I have a wire. I'll draw it over here. Okay, so I've got my little wire right here. And I have current flowing through it in this side on the left, out that side on the right. So we have current flowing through here. Now, my my current can be thought of as being broken up into a bunch of tiny little pieces that we're going to call ds, okay? So ds here may point like this, or like this, or like that, or back up this way, up this way. So those are all of my ds vectors, okay? We can break up this wire into little pieces that we call ds. Now what it says is that if I want to find the size of the magnetic field at some point, so I'm going to go, what's a good one to use? Let's go to this point right here. So the question is, what is the size of the magnetic field at this location? And we'll use a dB for it. That's what we want to do, is we want to find what is the magnetic field at point P. I'll just write that here. We'll call the magnetic field at that point dB. Okay. Now I'm going to use this ds vector right here. And what I'm going to do first is I'm going to draw an arrow from ds up to the point P, like this. And we're going to call that, you want to guess what I'm going to call this? What do you think I'm going to call this vector? That goes from the current element up to the point P. What would I call that vector? If you think about how I've done this in the past. Done stuff like this. R, that's right. This is going to be the position vector. Okay? R. Okay, so the size of dB, right, at that location is going to be given by this. Now, there's two parts of this. There's the direction, which is given by this piece, and there's the size, which is given by all the stuff in front of it, okay? Why is undo not working? I don't know. So the direction is going to be given by that. Let's look at that part first. ds cross r hat. Okay, so what is ds cross r hat gonna be? So you can see where ds is, you can see where r is. I'm just gonna say r hat would be a vector of length 1 that would point in the same direction as r, so it's gonna look something like that. Let's define the angle, the internal angle here. Let's call that phi. Call that angle phi. And then I can say that ds cross r hat is going to be equal to the magnitude of the vector ds multiplied by the magnitude of the vector r hat, and then multiplied by the sine of the angle between the two of them. Sine of phi. Okay. So the magnitude of ds would just be called ds. And the magnitude of r hat would just be 1, okay? And then sine phi would just be, well, sine phi. Can you tell me what's the direction of ds cross r hat? So this, well, all I've done here is just find the magnitude. What's the direction of ds cross r hat? If you use the right-hand rule. It's either into the page or out of the page. Which one is it? This one should not hurt your hand. You just need to take the vector from ds to r hat. So start from ds with your right hand, and then rotate your fingers to r hat. What direction is your thumb point? Point the fingers of your right hand in the direction of ds, rotate to r hat, your thumb should point out. Take a moment and verify that for yourself. A lot of people say an out, so a few people have figured it out. ds is this way, rotate to r hat, your thumb goes this way. Okay, so I said direction here, but really I was trying to figure out what this thing is equal to. The direction of ds cross r hat is out of the page. Okay, so we can go to this point right here, and we can draw a vector to represent our magnetic fields. It points out of the page. So we put a little dot right here, a little circle, and we say that's the direction of dB. Right? Okay. And then, in order to figure out what dB is, we would go back to our equation right here, and we'd say, okay, now we know that the magnitude of dB should be equal to something like mu naught I multiplied by ds cross r hat, which we just figured out was ds times the sine of phi. Whoops. ds times sine phi. And then we would divide by 4 pi r squared. And now, if we actually want to find the magnetic field at this point, we don't just need this quantity. We now need to add up all of the possible dBs that we can have, which is to say that we need to draw another vector from this point. Let's see if I want to be red. We would have to draw a vector from this point to this point. We would have to draw another vector from this point up to this point. Each one of these, as you can see, is the angle phi going to be the same for each one of these? Is the value of r going to be the same for each one of these? What do you think? Is the value of r for each one of these going to be the same, or are they going to be different? Is the length of that line is it changing? Yes, no? Is the length of this line changing? How long do I have to wait? Yeah, it's changing, right? So r is changing, right? What about the angle? Is the angle changing? The angle phi was the angle between r and ds, right? Is that angle changing? Is the angle here the same as the angle here? It's not, right? The angle's changing as well, right? Okay, so in principle, the current probably isn't going to change. 4 pi is obviously a constant. And, mu naught is just a constant as well. I didn't tell you what it is yet, but mu naught's a constant. So, ultimately, you're just doing this integral of ds sine phi over r squared. And we'll look at some ways that we solve it here in a second. We'll look at a specific calculation. But this is how you do it. This is how we find the magnetic field. It can be quite challenging. All right, I'm going to delete all of these lines here because I think it just makes things more confusing. All right, what would happen if I came to the other side, though? Suppose that I came over here to some point that we call, I don't know, point W or something like this. And now I want to figure out what's the direction of the magnetic field on this side. Well, I would have to draw an arrow from here to here. That would be my new r vector. And then, of course, r hat points in the same direction. What happens now? To get the direction, you need to do ds cross r hat. If you do ds cross r hat, what's the direction of the magnetic field at point W going to be? So do ds cross r hat. ds is this way. R hat is this way. Your thumb points in what direction? Into the page. So that means that the magnetic field on this side over here points into the page. And if you're sitting there thinking about this, you might realize that if I picked another random point over here, maybe we call this point Y, what's the direction of the magnetic field at this point going to be? How do you figure it out? Well, you have to take some kind of a vector, draw it from your wire out to this point. You see your ds vector, you label your r hat vector, and do it again. So this is ds. If you do ds cross r hat, what direction is the magnetic field going to point at point y? It's also into the page. Exactly. So you start to get this sense that any point that you picked over here, it would always work out the same, right? Would you all agree? If you really start to think about it? Pick another random point, draw another vector, you're still going to get the same thing. So it looks like the magnetic field is always into the page on this side. And you could extrapolate as well if you start working out over here. The magnetic field on this side of the page is also always going to be out of the page. Okay, so one thing you can do is you can say, suppose that I have a long wire and that wire is straight, let's say, and it carries a current I, then on the top side of the wire, the magnetic field is going to point out of the page. Okay. And so like on the left, like suppose you're driving along the road, and this is the road. On the left side of the road, the magnetic field is going to be coming out. And on the right side of the road, or on the right side of the wire, the magnetic field is going to be going in. I don't need to put circles around these, I can just put X's. And effectively, that's what this equation says. It's a very complicated equation. We're going to do some examples with it. You're not going to use it very much in this class. Mostly what we're going to do is we're going to use this to derive things. And then once we've derived them, you're going to use the results. But my point is that what this says, when it says ds cross r hat right here, what it's telling you is that the magnetic field above a current carrying wire is coming out of the page, and below a current carrying wire is going into the page as long as the current flows to the right. If the current switches and flows to the left, it switches. But, yeah. And this is how the magnetic field for a current carrying wire that comes out of the page goes in circles. Is that like the circles around I in red? Yeah, like right here, right? If you think about it, if I have a current that comes out and then goes back in, right? The magnetic field line kind of goes out and in. It goes out and in. It's like shoelaces, basically, right? This is the direction of our magnetic field. It comes up over the wire, like that. Going around technically back this way. Yeah. So a current carrying wire produces a magnetic field. It looks like this, or it looks like this, or it looks like this, however you want to think about it. All kinds of different possibilities that depend on how the wire is shaped. That is what's going to control the shape of the magnetic field is the shape of the wire, basically. So we're going to look at a specific example where we're going to have a long wire. It's going to carry current, and we're going to try to come up with an expression for the magnetic field of a long current carrying wire. That's what we want to figure out. Okay, so now we want to find the magnetic fields of a long current carrying wire. So we're going to take a long line and say that it carries some current that we call I. I guess it doesn't matter which direction it goes. Let's say the current's flowing this way. And let's say that we know the length of the wire from this point to this point. I guess I can use the same numbers that your book uses. So the numbers that we're going to use in this case are going to be current is equal to 125 amps. That number is out of control large. And we're going to find the magnetic field due to a... That's really weird. Now, never mind. We're not going to use the numbers that your book uses. So let's say that the length of my wire, L, is 2 meters long. And let's say that I want to find the size of the magnetic field at a distance away from the wire. I guess I'll call that X. That's equal to 1.2 centimeters. We're going to do that. Yeah, I don't understand what the book is doing. Oh, because they're separating this problem out from... I get it. I get it now. Okay, we don't even need to use these numbers. We're just going to find in general what the magnetic field of this wire is at some distance x away. So we're going to come right into the center, which should be like right about here. And we're going to find the magnetic field at this point. And I'm going to draw in here another line, maybe in dark color. It's going to go through here. Okay. So we want to find the magnetic field at point P. And we're going to use the Biot-Savart law to do that, which was this. ds cross r hat. Oh, I didn't tell you what mu naught was. So just so you know, mu naught is a constant. It's exactly equal to 4 pi times 10 to the negative 7. Okay, what is this one? Tesla meter per amp, maybe? I never remember. Yeah, that's right. Tesla meter over amp. Tesla times meters divided by amps. This thing is called, as a name, it's called the magnetic permeability of free space. Put in a less complicated way, this number tells us just how much space itself resists the formation of magnetic fields. It's a tiny number, which means you need a lot of current to produce a very sizable magnetic field. And it's a unique constant in the sense that it is exactly equal to 4 pi, not approximately. It's exactly 4 pi times 10 to the minus 7. All right. So let's go about finding the magnetic field at this point right here. We're going to learn later on in this class why it's exactly equal to 4 pi. Okay. So, all right, we want to find the magnetic field at this point. The current is flowing in this direction. The length of our object is L. There we go. All right, so we're at point P, a distance of x away from our object. And in order to use the Biot-Savart law equation, what we have to do is we have to come up to a point on our object, like for example right here, and we need to label a ds vector, which is going to be our tiny piece of current. Okay, so we're going to call this ds. That's going to be our current element, similar to the charge elements that we found early on in this class. We're now going to draw a vector from here down to here. Remember that you always draw the vector from the element out to the point. That's going to be our position vector r. And let's define the height of this right here to be y, which means we're effectively making it so that this is the positive x direction. This is going to be the positive y direction, okay? And yep. Okay, so first things first, what is the direction of the magnetic fields created by this current element here at point P? So do your right-hand rule and do ds cross r hat to figure out the direction. So ds is this way. Remember that r hat is a vector that points in the same direction as r. So we can just kind of like on here, draw a little r hat vector. What's the direction of ds cross r hat? ds is up. Use your right-hand rule. Yeah, ds cross r, your thumb points in. Now it's important to understand that I'm not going to draw my magnetic field here. We're drawing it at this point, okay? So let's just say that our magnetic field vector goes into the page, and we're going to call that dB. Now it's a good idea to go ahead and check that other pieces on the object have the exact same direction. So let's just check one more on this side just to make sure. So if I had a ds right here, and I drew an r vector like here, right? And then I have my r hat vector here. If I do ds cross r hat now, my thumb also points into the page, right? So ds is up, r hat is this way. My thumb also points into the page. So we know, lucky for us, that at every point along this wire, the magnetic field is always going to be pointing into the page. Can everyone see that? Again, ds, r, thumb in. Get used to doing that. If you're still not able to figure it out, you really gotta, don't be afraid and just try. Just try to use the right-hand rule and you'll figure it out. Alrighty, so now we want to apply our equation. And in order to do that, the first thing we can do is we can say we know the magnetic field points in, so we don't need to worry about this the direction now. And we can go through the same thing that I said just a second ago, which is that ds crossed r hat is equal to the magnitude of ds times the magnitude of r hat times the sine of the angle between them. Okay, so now I need an angle. The angle between ds and r hat should be this angle right here. Let me move this to the other side. Or even put it like maybe right there. So the angle between the two of these is going to be this angle here. So I'm going to go ahead and label that as phi. So we'll have sine of phi. But, oh, and then this is just going to be, ds. I guess in this case, ds has become dy, hasn't it? Yeah, because this is y, it'd be y plus dy. So our ds basically becomes a dy now, just because that's so s is the generalized coordinate in case it was curvy, but because ds happens to lie directly along the y direction, we can say that it's just equal to dy. In general, ds itself would always be equal to some dx I hat plus dy j hat plus dz k hat, at least in Cartesian coordinates. You could have a ds that you could write down in other coordinates too. But if we're only making changes in the y direction, then our ds now is just equal to dy j hat. And if I find the magnitude of this, right, the magnitude of this is just dy, right? That's why I say ds is just dy. The magnitude of r hat is 1, and of course sine phi we need to keep inside of here. All right, so now we know what ds cross r hat is. That's going to go directly into our equation there. Yeah, let's go ahead and throw everything together. So now we have dB, which we already know points out of the page, is equal to mu naught I over 4 pi r squared. And then we replace ds cross r hat with dy times the sine of phi. And now we can integrate. Except that we need to do a little more work. Before I do that, I'm going to stop for a second because I know I've done a lot so far. Does anyone have any questions? Okay, y'all want to tell me what to do next then? We've done plenty of problems like this in this class. You all should know what the next step is probably, or at least someone should be able to figure it out. What do I need to do next to solve this problem? Starting from this line right here. Maybe get dy into d theta, we could do that. Okay, so let's start working on that. First thing, you don't mean d theta, you mean d phi, but that's fine. First thing to do is to note that if this angle is phi, right, and I want to find the sine of phi, it turns out to be the case that if I find so this angle on this side is 180 minus phi, right? So it's pretty easy to prove that the sine of 180 minus phi is also equal to the sine of phi. So that means that in this case, since the sine of 180 minus phi is equal to x over r, we can just say that the sine of phi is equal to x over r. All right? And then I know you said you wanted to change dy to d phi, but let's see what happens if we do everything in terms of y. So, because I think this is going to be relatively easy to solve. I probably end up being wrong here. So according to this, then, x over r is equal to sine phi. And that's also can be written as x over the square root of x squared plus y squared is equal to sine phi. And of course we can use, I'll write somewhere up here, I guess, that r is equal to the square root of x squared plus y squared. So let's just write everything in terms of y then. So we're going to get b is equal to mu naught is a constant, I is a constant, 4 pi is a constant. And so we just have the integral of dy times sine phi. Sine phi was x over this. R squared is this thing squared. So I think we're going to get x squared plus y squared to the 3/2 power. Dy. Yeah, I guess I was wrong. We're probably going to have to convert this to angles anyway, aren't we? You know, or we can just, and we've done this before, and I would like to actually do some problems and stuff, so with only 20 minutes left, I'm just going to put the result. So this reduces down to b is equal to mu naught I over 4 pi. Do a trig sub, let y equal to x tan theta. You'll get dy is equal to something like tan squared, or secant squared theta. Do some things, and you're going to get, so we're going to be going from what? Negative L over 2 to positive L over 2, right? So for us, I think our answer is going to be L over x times x squared plus L squared to the 1/2. I think that's what we're going to get. Because in the book, they go from negative a to positive a. We're going from negative L over 2 to L over 2. So our answer should be the same as theirs, except multiply or divided by 2. Okay, so this is the result we get. I don't know how much you're actually going to use this result, but what you will use a bunch is what happens to this result when x becomes much, much smaller than L. So when x is much, much smaller than L, which is kind of what I tried to use here, 2 meters and 1.2 centimeters, then what we can do is neglect this x in favor of this. The L's will cancel out, and we're going to get mu naught. Oh, this isn't going to work out because I'm missing the 2. What does that matter? Why would that matter? Oh, I think I know what's going to happen. I think I know I did this wrong. Because it's from L over 2 to L over 2. This is going to end up being here. I made a mistake. Instead of L squared, this should be L squared over 4. Ugh, it's going to look awful. I'll try to get in here. This should be L squared over 4. 4. And then it should work, right? Yeah. If x is much, much less than L now, this is going to reduce down to mu naught times I divided by 2 pi times x. This is the result you all are going to use a bunch in this class. So this is the magnetic fields of, it's technically an infinitely long wire, but it'll be for pretty much all wires for us. But the key thing is this is a straight wire. So it's a wire that is straight up and down, okay? So we're gonna use this result a lot. And do I wanna tell you the other results, or are we gonna, I guess we'll derive the other result. All right, so we're gonna do 2 problems. One of them I don't even want to do almost because it's too easy, but we'll do both of them. One of them is really fast. This one and this one. And we might have time to do the other one. That'd be nice if we could. Okay, so let's see if we can do both of these. All right. So that's our result. Mu naught I over 2 pi x, where x is the distance away from the wire. That's what we're going to be using to solve this. It says a long straight conductor carries a 1 amp current At what distance from the axis of the conductor does the resulting magnetic field have a magnitude of B equal to 0.5 times 10 to the negative 4 Tesla, which is about that of the Earth's magnetic field in Pittsburgh. Okay, so we have a current carrying wire. It has a current that's equal to 1 amp. And we're supposed to figure out at what distance, so this is the distance we want to find, x, does the magnetic field have a value that's equal to 0.5 times 10 to the minus 4 Teslas. So we take our equation, which is magnetic field is equal to mu naught times I divided by 2 pi x, and we solve for the, we're solving for x, right? So we're going to get x is equal to mu naught I over 2 pi times the magnetic field B. If we plug in our numbers, the constant mu naught is 4 pi times 10 to the minus 7 Tesla meter over amp. We multiply by the current I, which is 1 amp. We divide by 2 pi, and then we multiply by the size of the magnetic field, which is 0.5 times 10 to the minus 4 Teslas. Plug these into our calculator. So we have 2 e minus 7, doing some of the math in my head, divided by 0.5 e minus 4. So we get 0.004, about 4 millimeters. Looks like you've got to be pretty close. So x was equal to 0.0044 meters, which is to say 4 millimeters. So some things to notice about this is the size of the magnetic field depends on the distance that you are away from the wire, x. It doesn't depend on x squared like it did for electric fields. It just depends on 1 over x. So the farther away you get, the weaker the field's going to be. The closer you are to the wire, the stronger the field's going to be. Any questions about this one? Okay, so let's do one that's a little harder. Magnetic field of 2 wires. Okay, so we have 2 wires, each one carrying the same current I but in opposite directions. So we're going to start off by drawing a line like this. And then we're going to draw currents on here. So we're going to have one current right here that's coming out of the page. We'll call that one I1. We're going to have another current that's on the same line. Let's put it like right about here. We're going to call that one I2, but we're going to say that they're equal to each other. So I1 is equal to I2 is equal to just I. We'll call them both I. And what we want to do is find the magnetic field at points P1, P2, and P3. You can't see it on the picture, but what we're going to do here is we're going to say, define the distance between this point and this point to be D, this point and this point to be D, and then we're going to come out to here at a distance away that's 3D, and then we're going to come over here at a distance that's 1D. So this is going to be 0.1, this is going to be 0.2, and this is going to be 0.3. We want to find the magnetic fields at 0.1, 0.2, and 0.3 due to wire I1 carrying current I1 that comes in and out of the page. This is going to be an infinitely long straight wire. And then the current I2, which goes into the page, another infinitely long straight wire. And the only equation we're going to need for this is B is equal to mu naught I over 2 pi times x. I may write this equation from time to time with an R in it, but it means basically the same thing. Okay, any questions about the setup of the problem? Let's do directions first. Okay, I'm just going to put the this little picture up here. If I have a current I1, like this, and I take my fingers and I point my thumb in the direction of the current carrying wire, I want you all to do this right now. Take your thumb, point your thumb out of the screen like this, and then take your fingers of your right hand and think about the direction that they wrap. Hopefully all of you agree that if your thumb is pointing out of the screen, the fingers of your right hand are going to wrap in a counterclockwise way from your perspective. That's the direction of the magnetic field. It creates a circle around this, and that's the direction of the magnetic field. Okay. If I have a magnetic field that points into the page, like wire 2 right here, where the magnetic field's going into the page, you point your thumb into the screen, and your fingers are going to tend to rotate in a clockwise way from your perspective. I'm not talking about what you see my hand do, so you have to do this yourself. Take your thumb, put your finger into the page. Your finger wraps like this. So if we take this circle right here, the magnetic field for this one is going to point opposite. Try to center it a little bit better. And so the magnetic field for this one is going to point like this, exactly the opposite of the other one. Okay, you get these circular magnetic field lines, and we're going to use those to figure out the direction of the magnetic field here. So I want you to tell me, due to current 1, right, what's the direction of the magnetic field at point P? Due to current 1, what's the direction at point P1? What is the direction of the magnetic field there? We don't have much time. You got to answer fast. It's down. That's right. Okay. What's the direction of the magnetic field for current 2 at the same location? So we'll call this one B1. What's the direction of the magnetic field for I2? You can either use your right-hand rule, or you can think about the way this looks up here. Yep, it's up. And which one is going to be bigger? Think about this equation. Which one is going to be bigger? The magnetic field B1 or the magnetic field B2? So some people are saying 1 and some people are saying 2. How do we figure it out? How do we resolve this dilemma? Look at the equation. Mu naught, I, and 2 pi are the same for both of them. So the one that is, what is it going to be, closer or farther? It's going to give the bigger magnetic field. It's closer. Yeah, closer. X is bigger, B is smaller. So for I1, the distance to I1 is 3D. What's the distance from point P1 out to I2? It's 5D, right? D, 5D. Okay. So that means that B2 will be smaller than B1. All right. Maybe we go one at a time. I don't want to do too much at once. We'll come back to doing the directions for the other ones. Okay, so point P1, we have B2 pointing up and B1 pointing down. So I'm just going to say that the net magnetic field should be equal to B2 minus B1. Okay. And that the size of the magnetic field B2 should be mu naught times I. They both have the same current. Remember, I1 equals I2 equals I. Divided by 2 pi. And now I need to put B2. The distance from I2 to point 1 is 5D, as was stated. And we subtract from that B1, which is going to be mu naught I over 2 pi times just 3D. Right? So this should be equal to then mu naught I over 2 pi times, what, a fifth minus a third. So 3 minus 5 would be negative 2, which would cancel out with this. So I think you're going to get mu naught I over 15 pi, and there'll be a negative sign indicating that it's pointing down, which is what we want. Okay, do you all agree with that? I'll let you kind of work it out yourself there if you want. Okay, point P2, which is right in the middle right here. What is the direction at point P2 for the magnetic field created by I1? Up, yeah. The way I think about it is, for I1 here, I know that it's going to create a magnetic field, and I know it's going to go around in a circle. And the question is, at this point, is it pointing up or down? So you take your thumb and you think, okay, it sweeps around like this. So at this point, the magnetic field has to point up. You can also compare to this picture over here on the right. I know people in the past, what they've done on tests is they've drawn like these two pictures and just used that as a way to help them out. Okay, so we know B1 goes up. And compared to the other B1 that I drew over there, it should be bigger because we're a lot closer to the current now. So that's B1. What about I2? Does it point up or down at this point? At this point, at point 2, what's the direction of the magnetic field for I2? Also up, right? And these two should be, what, the same size, the different size? What do you think? They should be the same, right? You're exactly the same distance away in both cases. So the size of the magnetic field should be the same because the distance is d for each one of them. So at point P2, we're going to get B net is equal to B2 plus B1 now because they point in the same direction. So that's going to be mu naught I over 2 pi d plus mu naught I over 2 pi d, which is equal to mu naught I over 2 pi, just over pi times d. Okay. 6 minutes left. Okay, going straight to point 3. What's the direction of the magnetic field created by I1 at point 3? Is it up or is it down? It's going to be up. It has to be the same direction as this one, right? Because we're on the right side. And now the magnetic field for so this is B1. And for I2, is it going up or down? I2 is down, that's right. Which one is bigger, I2 or I1? Or B2 or B1 is bigger in this case? Should I make this one longer? Should I make it shorter? B2 is bigger, that's right. So that's my picture now. And so for point 3, we'll write this one over here. For point 3, we're going to have B1 minus B2. I'm taking the up direction to be positive, by the way, if that wasn't obvious. Call that positive y or something. B1 minus B2 is going to be equal to B net. Well, it's not working. Let me undo. That's fine. I'll just do that. Okay, this is going to be B net. And so that's going to be equal to B1 is going to be mu naught I over 4 pi, or 2 pi, times the distance from here to here, which is d, so 3d, minus B2. B2 is a distance of d away, so minus mu naught I over 2 pi d, because from here to here it's d. And that will be equal to so we have a third minus 1, which will be equal to 2 over 3. So we're going to get mu naught I over, one of the 2's is going to cancel here. And that's going to be the net magnetic field at point 3. So this was point 2, this was point 1, this is point 3. Does anyone have any questions? Do we have time to do the hard version? We do. Okay, so keep that all in mind. So now the question would be, suppose that I have this problem. We have the exact same scenario that we had a second ago. So we've got our two objects. We've got our I1 here coming out of the page. We've got our I2 here going into the page. So now the tricky part comes when I want to find the magnetic field at a point like here. Okay? So let's say that I tell you the distance between here and here is 4 meters. I tell you the distance between here and here is 3 meters. That is to say from here down to here is 3 meters. Now if you want to find the magnetic field at this point, it gets quite a bit more complicated. I'll show you how you do it though. So let's say we want to find the magnetic field at point P. So now what I have to do is I have to come to this point right here, and I have to draw the direction of the we'll draw some extra lines on here to make this easier to understand what's going to happen. So now I have to go to point P, right? And I have to draw a vector for the magnetic field of both of these. Let's do I2 first. Can you all tell me what's the direction of the magnetic field at point P for 2? What would B2 point here? What direction is it going to point? Clockwise is not the answer. It has to be left or right. At the point P, what is the direction of the magnetic field for I2? Right, that's correct. So again, you're thinking of a big circle that goes clockwise, as you said, and at the top of that circle, if I draw a line from here to here, that's the direction of the magnetic field for B2. What about the other one's a little bit harder? So this is going to be the magnetic field for 2. What's the direction of the magnetic field for I1? This one's not going to be as simple. The answer is not up, down, left, or right. It's something in between. So current coming out of the page, right? You take your thumb and you point out of the page. It tells you that the direction of the magnetic field should lie along a circle, right? I'm going to draw a circle in here to help you see what this is, what's going on here. It should lie along a circle that's centered on I1, like this, right? Like this. And it should go, would you all agree that the magnetic field has to kind of go like this? Because it has to go around in a clockwise circle, right? So at this point right here, we have to draw a tangent to the circle. We have to draw a tangent to the circle at that point to get our B2. So I believe it will point tangent to the circle, right? So it's going to point up like that, where it's going to create a right angle right there. And now I'm going to get rid... Can everyone see it? I'm going to get rid of the circle now, because we don't need it. It was just a tool. Okay, so getting rid of the circle, that's the direction of the magnetic field at that point for B1. And now, if I want to find the total magnetic field, I have to vector add these, right? Which means I'm going to have to find components. You'll see this stuff show up on your homework. You all know how to do this stuff, though. Once you actually have the vectors themselves, they're just vectors. And now you just need to sum the vectors. And that means find components and solve for them. You know, solve for the total field. All right, does anyone have any questions? Hopefully that sets you up to where you can start to work on not only the homework that's due tonight, but then there's a homework that's due in 2 weeks. And this stuff that we've talked about just now should help you to get through it. Big new idea is just this topic right here, this concept right here. The magnetic field of an infinitely long straight wire. That's the new topic. Okay, we're out of time. I'll see you all on Wednesday. There's a lab this week if you haven't already done. Let's see. Has everybody done E5? I don't think so, right? Here, let's stop the recording real quick.